So first of all, I would like to thank the organizer to give me the opportunity to talk for one of the first time about some recent work that we have done, namely using electromagnetic showers to possibly produce paraplasma in the laboratory. So I like to say that it's a work that is a fruit of a collaboration with some École Polytechnique and the Sorbonne University, and that represent actually a big fractions of this grad students, Mathis Pouillet, that is a graduate soon, probably in October. So first of all, let's jump immediately in the topic and what are the goals and challenges. They're actually pretty basic. Let's assume that you have an electron beams, ideally not necessarily from an accelerator, but for something that comes from a plasma-based technology. So we have an electron beam, and we have either an intense laser, could be a petawatt laser here, or a target where you can vary the width and also the Z number. So they're gonna, here is the counter sending setup, and here you will impinge the electron beam on the targets, and on the rear side you will observe the beam, what is left from the beam, plus some pairs, and the same thing here. So the question is, yes, we've been producing pair in the lab, but can we produce a paraplasma? So we will show some analytical theory where we can produce, I think, pretty much accurately the number of pairs. We can estimate the volume, and we'll answer the questions in terms of, is there enough skin depth, the bi-length, and so on. So to address these questions, I would like to tell you about what I really call electromagnetic showers. What is the history of showers? It's a problem that started almost like 19 years ago. So what do we care about radiating theory if there is actually several? I will present the new methodology that we've been approaching, and then applying this methodology to strong in strong fields, which is a strong field here. The lab will be the laser, or in matter, which is the high Z target. So first, introductions of showers. So here in those showers, I will tell with 4 processes, which is a bit like the mayor. So in a laser field, it has actually been presented by David Rice this morning. We will have what we call the nonlinear compton scattering, which is a bit the same thing as a quantum synchrotron for the people of astrophysics. And then this gamma can decay into a pair. In astrophysics, it will be in a B field. Here it will be in the laser field itself. Now, in an IZ target, you have the mirror process. You will have the Bremsstrahlung, where an electron will approach closely to the nuclei, to the high Z, and produce a photon. This photon can do the same and produce a pair. This is the Bethe-Heiler process. So if we apply now, if we now have a cascading process, then it's an electron generate a photon, generate a pair, generate a photon, and so on. We can have what we call showers in field, but also be careful, this is not what we call QED avalanches, where you can have certain kind of topology where the second generation could be reaccelerated and reproduce pair and can reaccelerated, and this will give an exponential growth. Here, it's really the decay of an energetic particles, and every single new generation has less energy than the first one. So this is not an exponential growth, okay? So today, again, I will talk about EM field and matter. This has been published this year, and there's another paper under review. So the history of electromagnetic showers. So it starts, so there's almost 3 papers the same year. The first one's Carlson and Oppenheimer, and there's Baba and Heitler in 1937. That first have a bit of a sketch of how to deal with electromagnetic showers, which is really only the process of Bremsstrahlung and Bethe-Heiler. Next year, Landau proposed a much more rigorous formalism, where we'll use what they call Merlin transform. And this is very beautiful, and it allows you to extract the first analytical solutions. The problem is that it's a little bit, when you're doing a Fourier transform, it's easy to go to the Fourier space, but you have to go back in the real space. That involves usually very complicated inverse transform. And this is what Landau proves, that in some part, it can extract an analytical solution. The problem in this, the spectrum that you observe with the pair is only restricted to like a band of energy, and it's only for a certain time. So if you really want to know the multiplicity of your plasma number of pairs, you cannot. You just have a piece of the spectrum. I don't have time to show you this, but if you want, I can show you exactly the pure comparison between Monte Carlo and the Landau's work. And Akiezer in the 94 applies exactly the method of Landau for showers in a magnetic field. Okay? So in the next decades, people are saying, we're not going to talk only about the spectrum of the showers, but we want to know the angular distributions, also what happens when you have multiple scattering. So basically, what is the shape of the shower at the exit, okay? And what we have done here, and first of all, so this has been study for many decades, and more recently, so using here plasma technology, Gianluca Sari sent an electron beam in a high-Z target and observed almost a quasi-neutral pair plasma, which means the radius of the jet was under the skin depth. And more recently, and you're going to see this afternoon, using the CERN, and this is a gamma seeded, where here you have high multiplicity. They're definitely very close to your plasma. But, so we have a lot of tools, numerical tools to analyze this, but I think there's a lack of a theoretical model to get some quick intuitions about how the shower develops. And this is what I'm going to present here. So first of all, showers can be encountered in many places. So you can start, as you say, with an electron beam that impinge an RZ target. And this is typically Gianluca Sari and Harold Smith in the Nature Communication of last year. You can have a laser that goes into a high-Z target, will generate hot electrons. Those hot electrons will generate pairs. An example here of a simulations when you have a very strong petawatt laser, create pairs, and then you can guide those pairs in the channels. Or typically use a very, very strong, let's say almost a kilojoule, a laser that goes on the golden target, same process, generate hot electrons and a lot of pairs. Huichen has been studying this extensively for the last decade. You can also have what David Rice was talking about. You want to do not only matter, but you want to do strong fields. So you have this is the famous seminal experiment from SLAC. Ideally, you will have, at the time, I think the A0, which is, the intensity was about mildly relativistic. But nowadays, you can go 4 orders of magnitude. So you really have a strong field, and you want to counter propagate a very strong electron beam. Or there's also a different kind of setup here when you can basically self-reflect your electron beam with a laser with a plasma mirror. Anyway, or even more at the interaction point of a collider. So imagine that you can have a pipeline with, let's say, 50 stages of plasma accelerator, and you will get at the end 1 TeV. You collide with 1 TeV. The beam is so dense, so energetic, that the self-beam of the beam either triggers a cascade at the interaction points for the showers. Okay? So what is the new methodology compared to what has been done in Landau? So I remember the challenge in Landau that he has a piece of the spectrum. But if you really want to know if you have a plasma, you need to examine the exact density. So what we're going to do is that, first of all, the formalism of QED showers. So I'm trying to put as few equations as possible. I still am going to leave some in the talk. So here, this is the time evolution of the pair spectra is due to the fact that you have photon emission. So your function distribution is cooling due to the photon emission, but you have new guys popping up that are the pairs that are populate your distribution functions. On the other side, you have the evolutions of the spectrum of the photons. So they have photon emission from the lepton, but you're losing photons because you're creating pairs. Okay? So typically, regardless if we have nonlinear Compton scattering, Bremsstrahlung, or Breitweiler or Bettheitler, the spectrum will look a bit like this. It reminds you also, if you want, a synchrotron spectrum. Okay? And when you're going to create a pair, you will have typically those kinds of pair production spectrum. So those are the equations. This is what I call a bit like the Vlasov part. This is the time variation of the distribution functions. Here you have the fact that you can produce, that you're emitting photons. So you're shrinking in phase space. And now you have those photons that are creating pairs. Same thing for the photons. The time variation of the distribution function is, so now you have a plus term that is coming from the photon emitting by here, and you have a loss term because you're losing photons due to the fact that you're creating pairs. Okay, so what we did here is that when you imagine yourself, and there was a diagram by Alice Harding, to have a cascade, you have an initial particles that creates a photon, then create a pairs, and you have this tree coming, okay? And you have the 0 generation, first generation, second generation, and so on. So what we're going to do is we're going to split the distribution functions in every generations. So the 0th is actually my beam. The first will be the first pair, then the second pair, third pair. And what we're going to do is we're going to insert this in the equation that you saw before. And what we're going to see is that basically the pair spectra of n is due to the photon of n, and also to the pairs of n minus 1. You're going to do the same with the photon. And now the trick is that we're going to say there's a lot of manipulations that you can express basically that the generation, the number of pairs n plus 1 is a very, very complicated functions of the things of n. Now imagine you can integrate this. If you sum over all the n, you have exactly the multiplicity of your shower. So there's one very important time here, is called the radiation time. So this radiation time is not the photon emission time, but it's the time, a little bit like the stopping power, is the time at which basically a particle loses almost all of its energy. And you can derive it like this. If you prefer in terms of space, you can define the radiation length, which is just the radiation time divided by c. So I spared the math. It's very long and tedious. If you want, I can show you. But you can extract two exact analytical solutions. So first of all, what we call short time is when t is small compared to the radiation time. The multiplicity will be L over L squared times the complicated functions of gamma naught. And for the strong field will be the same thing with a function of chi naught. I'll tell you in one moment what is the chi naught. For the very long time, you will have n plus O n naught is proportional to gamma naught, and this you can expect it intuitively. If I have a particle that has gamma naught, imagine I split every time in two. I will gamma naught divided by 2, gamma naught divided by 4, and so on. At the end, the best that I can have is gamma naught particles. But there's a factor in front that comes from the theory. Same thing for the strong field. This multiplicity will be exactly proportional to chi naught. So now I'm going to apply this methodology for two kinds. Once again, you will see the strong field, the showers in strong field when we have an electron beam counter-propagating with the laser. The second will be an electron beam that I shoot on a high Z material. So this is the setup that you really have in mind. The dimensions are not exactly true, but you will have, let's say, typically an electron beam. You can imagine that this is few microns long, few microns thick. The gamma naught will be very big compared to 1, so typically GeV beams. I have a laser here. So for some people that are particular, this is the intensity parameters, which represents also how relativistic the electron is wiggling in the laser fields. This is the laser focus, will be also a few microns, and the laser, let's say, a few femtoseconds. After the interactions, I end up with another thing, where here I have what is left from the electron beam plus the pairs. So I think this has been introduced by David Rice this morning, but I will say, so what is strong field QED in a nutshell? There's one very important parameter, it's the chi parameter, which is simply the ratio of the transverse Lorentz force to the Schwinger field in the rest frame of the particle. So here, this is the formula, and if you apply this to a counter-propagating setup, so you have only the field of the laser, the gamma naught, and you find that is 2 times gamma E naught, which is the field of the laser, divided by ES. In an engineer formula, it will look like this. So the energy of the beam in GeV multiplied by the square root of the intensity in unit of 10 to the 22. 10 to the 22 because it's typically what we're going to use for petawatt laser. So if you want chi on the order of 1, it's very easy. 10 to the 22, 1 GeV. But you want chi much bigger than 1, and you will see why. So you're going to play with what? So with a typical base plasma accelerator, this can go up to 10. But maybe here we can maybe crank up to 10 to the 23. So we can probably approach chi 20-ish, 30-ish in the near future. The conditions to have significant pair productions is chi bigger than 1. Okay, so now you know strong field QED. Voilà. So now I'm applying this, all the methods to, again, so here I took gamma naught equal 10 to the 5. I didn't really put a real laser, I put a B field. But you can put any kind of cross field, it will give you exactly the same result. So the chi naught initially is 1000, and the radiation time is 1 femtoseconds. So here, this is the shower multiplicity. This is time in units of the radiation time. So you can see here that exactly at the radiation time, the average energy of my beam, exactly, lost almost more than 99%. Okay, so the blue term is the average energy during the interaction. Here, in red is a Monte Carlo that solves exactly the kinetic equation that I presented before. And here are the analytical solutions with the splitting method. So we see at early times, t over t squared times a function of the chi naught. And at long time, it's chi naught times a function that will never grow very big. It's a log. Okay, so you can imagine that this basically is on the order of chi naught. We can also verify that our theory works well. So this is the number of pairs, again, the Shell multiplicity as a function of chi naught for the short time. So this was already derived by Tom Blackburn in 2017, and we added this new term here just to show you that it pretty much works all the time unless t equals tr. And which is funny is that Landau obtains the good results when t equals tr. So now we know pretty much all the solution. So now, do we really create a plasma in a beam laser interactions? So first of all, remember, the conditions for quasi-neutrality implies chi bigger than 1. because my multiplicity is on the order of chi. So the bigger the chi, the purest is my electron-positron plasma. So chi equal 1 implies GeV beams and 10 to the 22. My radiation time will be this formula. So imagine this is maybe 10-ish, but this is also a big number, so I still remains on femtoseconds. Yes. So I will have to use a laser that has at least 10 femtoseconds, which is pretty fine. So now the analytical density. So n is number of pairs divided by the volume. I will take that the final radius of my pair jet is on the order of the width of my laser beam, and I obtain n plus is about 3 chi times this. Okay? So if I plug this, and I can estimate, I don't show you here, but I can estimate the final gamma of the pairs. So far, with those numbers, I'm still that the thickness of my pairs is on the order of skin depth. So I'm still not exactly, but if you could crank over those numbers, we could probably reduce the delta compared to RB. So now I still have 5 minutes, and I'm going to finish with electromagnetic showers in matter. So this is the setup. We use the same electron beam. You can choose the L, you can choose the Z, from Z equal 1 to 100, whatever you want. Here, what is the requirement to optimize the density? So be careful. Pair production increases with L, it also increases with Z, is increased with gamma naught. But this is actually a very divergent pairs, as you will see, because there's multiple scattering in the targets. So as you scatter more, the density will decrease. So you will be, there is a kind of a trade-off on optimizing the L and the Z. So again, I'm applying the same machinery of the photon splitting. I'm showing typically shower multiplicity as a functions of the target length. Again, so here I pick 73, 10 GeV beams, and I put, so n, the multiplicity L over square, times a complicated function of gamma naught, and at the end, there's the maximum number of pairs can you obtain if you have gamma naught. So the exact result is 2 plus lambda divided by 2. Actually, with in a Heitler paper, he thought that number was 3, that he was a bit of a guess. So be careful. Actually, you cannot only consider 2 processes in the target, because when you have multiple scattering, pairs become trapped in the target. So you cannot really extend your thing for too many radiation length. Okay? So you have to be in mind that this is an analytical result that do not really exist in reality. So once again, we're going to do the same thing. We want to consider that we have this kind of cone at the exit. We know what's the angle, we know what's the radius, and we can calculate exactly what's the density of the pair plasma, and we can even derive this and find that the number increased with L over R, but the volume also increased with R and R, so there's a maximum density that is given by this. Now we can ask ourselves that if you want to produce them, you want the thinnest possible targets. So looking at all the periodic elements, we want to find the smallest radiating length with gamma naught, and we found that actually the best material is iridium and the neighbors, which is around here, and you will get a maximum density higher than lead. But actually, if you're very rich or if you're poor, you don't want to use this. It's a very expensive material, and you better just work with lead. Comparison with Giant 4. So Giant 4, I'm not going to in the detail. It's a code that is used like Fluka to calculate all those kind of showers. And I want to show you here the analytical formula that we obtained for the pair density as a function of L over LR with typical numbers of plasma-based accelerators. Initially, be careful. This is the pair density, but the plasma is non-neutral because you need to reach a point where we start to have at least n plus much bigger than n0. And I'll show you the point where this is about 2. So this is almost quasi-neutral, and it gets the more you go here, the more you get neutral, okay? And I'm going to show you also the question, is it really a plasma? So I'm plotting here the skin depth. So this is the result from GN4. This is the analytical formula. And I'm showing here the radius and L over R. So we'll say that here, there's a point where the skin depth becomes lower than the radius of the exiting pairs. So this is actually quite of a good region. You're not exactly quasi-neutral, but you're going towards it. Yeah. And so basically, you will have almost a quasi-neutral plasma, and you start to have positively observing collective effects since your skin depth is smaller than the radius of the beam. Those are engineer formula, but I don't have time to explain them. It's not very important. Just to show you, those are quasi-ideal pair plasma conditions, and lambda by cube, regardless of the parameter, is on the order of 10 to the 9 or 10 to the 10. So you really have quite of an ideal plasma. So to conclude, we have this new framework for modeling strong field showers in matters and strong field theory, strong field. There's two regimes of evolution that depends on the radiative time, or short time solutions and long time solutions. So if you have a strong field, I will tell you maximize the beam energy and the laser intensity. If you're in matter, work around Z equals 75 and don't go above L over radiation time. The future directions. So we like to do now extensive self-consistent simulations in 3D to verify the validity of those kind of ideal conditions. So in more relative conditions, and maybe to investigate also beams that are not monoenergetic, that comes from DLA. Thank you.
Okay, thank you, Thomas, for this very nice talk and excellent teaser for the session we're going to have this afternoon. As the talk is now open for questions, I'm going to come to you over there because you are straight up, and then I'll come back to Dimitri.
Thomas, thanks for the great talk. I apologize if the question is too stupid, but what's the fate of these pairs? In other words, how long they survive? And is there any possibility to accumulate them and trap them from multiple of these shots?
So the question about the only way to disappear, if they could reannihilate or they will just spread out. So you will need to have like a diagnostic that is actually another part, not too far after the interactions. Okay? Yes, some people think about putting some magnetic field maybe to recompress or collimate those pairs to form something even denser.
But I guess to avoid reannihilation, you probably want the opposite of that.
Be careful that, so in the first part, in the first setup, the pairs are almost produced in a collinear manner with the beam. So they have almost no angle. In the second, the angle is clearly, it's called to the Molière theory and everything, there's a much bigger angle. But I don't think and also they're extremely relativistic, so I don't think they collide that much. In the first case, they're really collinear. It's really, it's even smaller than the beam. It's really like a little tube inside the laser beam that's coming out.
So for now, if you want to do any sort of plasma physics on that pair
so,
plasma.
You will see this, I think, with Gianluca Gregori and Aerosmith. What they want to do, for instance, is could you see typically plasma instabilities like parafilamentation? Imagine you're exiting this and you put this in a stable plasma and you're looking at all the beam instability. This will be an example.
More about that later, I think.
Thank you very much, and thank you, Thomas, for a very beautiful talk. Enjoyed it very much. If you could go back to the last slide of your section 4, which is just before, just on magnetic field production.
Okay.
And the condition for, well, the next one, I think this one, right? So or is there another one after that? Sure. No, okay. So showing the results, going back to Ike's question. No, okay. So the plasma condition, right? This delta comparing to the beam size. So what's what is the result? So how far are we from approaching this condition?
So you will see this afternoon that I think they have. So they are not here. My constraint is to use an electron beam, and ideally something from tabletop, where this will come from a plasma bubble. So I think this is something standard. If you have a petawatt laser people produce, and you have to imagine like a small ball micron size with already this is a bit pushy. People will have more about close to nanocoulomb. I pushed the number to a nanocoulomb beam, which is about 10 to the 10 particles. So now from this, I can have, if you can calculate the chi, because I didn't put the A naught. So imagine now you can put a laser, you will obtain the chi. This will typically be the density of this jet coming outside, okay? Right, and then this gamma plus is the Lorentz factor of fluid of the pair that are coming outside of the interactions.
No, I understand. What are the resulting numbers after
whatever you put here, so see RB is on the order of a micron.
So it's I mean, when you say equal or less, does it mean that you're approaching it? We are now approaching it.
I cannot find this bigger.
You cannot find this bigger?
No, I'm on the same order.
Same order.
Maybe a factor of 2. Regardless of the number, you can play around. You always with this.
And is this in the? I mean, as you said, this whole beam moves relativistically, right?
Yeah.
With what typically? What's the Lorentz
So
factor of the
initially,
beam?
you started, let's say, with the
Can
gamma.
one go into the beam reference frame? Oh, the pair.
Oh, no,
the pair
here you
plasma.
need to take the fluid one.
Right, right.
I'm not talking about the bilength here. I'm talking, so imagine here you have 10,000 or maybe a few thousand. You have typically a radiative time, so you lost 99% of your energy. You can estimate this about 100. If you were here about 10,000, this will be 100.
So what I mean is that this is Lorentz factor in which frame?
In the lab frame.
In the lab frame, right?
Yes.
But I guess to study collective phenomena, what would be interesting to see what is it in the frame co-moving with this plasma, right? In the,
yes, but actually,
this
has been done also. I think, well, I have to admit that we can do it exactly. So you are in the co-movement. It doesn't change this. Actually, this is what actually was spotted by Gianluca Sari when they were in even small number, and I think they obtained delta is 2 times RB or 1 RB exactly. So that's
right.
They were, but I think they were estimating this with the Fluka codes, but we re-encountered this result exactly. So I think we need probably a higher charge or high energy to start to have this decreasing and this being increased a little bit. So, but so far, I would say that they are not the greatest tool to produce a pair plasma. You can probably study strong field QED, gamma ray sources, but it doesn't look that this is exactly a plasma in terms of quasi-neutrality and skin depth. The other ones,
the other one is
the one seems to be much more promising. Yeah.
Right. Okay. Thank you.
Are there further questions? Okay, I get to ask something. So you mentioned when showing your results for the shower in matter that if you go too thick, then the pairs can't escape. And presumably this could also happen in a laser pulse. If you want to be
exactly.
enough,
So
right?
there's so many details that I didn't talk about. If the gamma naught, if the gamma is on the order of the A naught, you may have actually reflections in the laser. That's why usually you start with the gamma naught that's maybe orders of magnitude, and I think most of the pairs, after a few femtoseconds, will still be able to cross the laser. But we know from radiation reactions that they have those very phony orbits when particles are reflected inside the laser pulse if they don't have sufficient energy. Correct? Or?
Would that be useful for making lots of pairs, or?
I don't know, because it's not a jet anymore. You get pairs coming sideways, maybe at 90 degrees, and now they're not directed anymore. So here you can really see that, they become trapped inside the target. So that's you don't want to have actually the ideal says more events, more pairs, but those pairs are cold and are just bouncing inside the target, so you don't even see them.
Are there further questions? If not, then let's thank Thomas again. Thank you very much. And thank our next speaker.